Hi there and welcome back to the College Physics series. In today's video, we're going to be talking about motion in two dimensions. We're going to attack the concepts heavily, so we're not going to be solving a lot of problems, but these concepts are important for you to build a foundation in understanding two-dimensional motion. Thank you for being here. Let's get started. In one-dimensional motion, we only consider movement along a straight path, but most real-world motions are two-dimensional. Imagine a car moving along a curved road, a soccer ball being kicked at an angle, or a roller coaster speeding along a winding track. These are all examples of motion in two dimensions. Two-dimensional motion involves movement along two axes, the horizontal x-axis and the vertical y-axis. Since we need to describe both the magnitude and direction of the motion, we use vectors. Vectors are essential because they allow us to represent motion in any direction. In one-dimensional motion, displacement is simple. It's just the straight line distance between the starting point and the end point. But in two-dimensional motion, displacement happens in a plane. For example, if a car rounds a curve, its displacement vector connects its initial position to its final position. The actual path of the car might be curved, but displacement is just a straight line distance between the 2 points. To describe displacement in two dimensions, we break it down into its x component, which represents the horizontal displacement, and the y component, which represents the vertical displacement. Using trigonometry, we can calculate these components if we know the angle and the magnitude of the displacement vector. An example of that would look like this. So let's say this vector has a magnitude of 100 meters and it's at an angle 30 degrees above the x-axis. These are examples that we've seen before, where we can break down the vector into its y and x components. So let's see a quick example of displacement in two dimensions. This motion diagram would represent a car driving along a curved road. In blue, I can draw the displacement vectors between each frame. Notice in the beginning, the size of the vectors here decrease. That means that the object would be slowing down. As the car goes around the curve, the size of these vectors remain relatively similar, meaning that the car is moving at a constant speed. When it goes along the straight path in this section, the size of the vectors start growing, which means this object is speeding up or accelerating. This type of motion represents a motion that occurs in a plane or in two dimensions. A plane is a geometrical idea that you might remember from geometry, where we represent a plane as a four-sided object, but in reality the sides of the shape extend infinitely left, right, up, and down. So I have this entire plane to work with, where this object can move this way, this way, this way, in any direction it pleases. That's the main difference between 2D motion and 1D motion. In 1D motion, the object would be limited to moving along left, right, or up, down, like these red arrows. Now let's move on to velocity. Just like displacement, velocity in two dimensions is a vector. It has both an x component and a y component, and the direction of the velocity points in the direction of the displacement. The formula for velocity in two dimensions is similar to one-dimensional velocity. We write it as velocity is equal to the displacement divided by the time interval. Since this is a vector, it has a magnitude and a direction. The magnitude is just simply the displacement divided by the time. And the direction, like we just wrote down, is the same direction as a displacement. Coming back to this example of a car driving on a curved road, I can draw the velocity vectors similar to the way that I drew the displacement vectors. Remember, the velocity vectors point in the same direction as a displacement. So I'm going to get a very similar looking diagram when I draw the velocity vectors and compare it to that of the displacement vectors. So I get a very similar looking diagram. It should be the exact same diagram. Again, we get this because velocity points in the same direction of the displacement. Next, we have acceleration, which is also a vector in two dimensions. It tells us how the velocity of an object is changing, either in magnitude, which is speeding up or slowing down, or in direction. When motion is two-dimensional, acceleration can occur in both directions, horizontal and vertical. Now here's where vector math comes in handy. You can find the acceleration vector by subtracting the initial velocity vector from the final velocity vector. And this is how we write the equation for acceleration in 2 dimensions. Acceleration is equal to the change in velocity vector over the time. If I want to find this change in velocity vector, I need to do the final velocity and subtract it by the initial velocity. Notice how they have the vector symbols on top of them. That means that they are vectors. They're arrows that I can graphically add or subtract tip to tail. Let me walk you through how to do this using vector subtraction. First, draw the initial velocity vector vi. Now let's say we have an example where this vector is vi and this vector is vf. Step 2, then draw the final velocity vector vf as shown. Step 3, to subtract the vectors, use the tip-to-tail method. Place the tail of negative vi at the tip of vf, and the result will be your change in velocity delta v. So let's see how we do this. First, we are going to take vf. Then we're going to draw negative vi. Since vi goes forward towards the right, I'm going to draw, starting from here, forward to the left. And this would be negative vi. Remember, when you multiply a scalar by a negative, you're going to reverse its direction. My resultant starts at the tail of my first vector and heads into the direction of the tip of the second vector. And this yellow arrow will be my change in velocity vector, delta v. The resulting vector points in the direction of the acceleration. Because we said over here that my acceleration is equal to my change in velocity vector. So that is exactly what we have found right here. This technique is particularly useful when an object is turning, such as a car rounding a curve. If the car is slowing down, the acceleration vector points inward toward the center of the curve and opposite of the velocity vector. Let's see this idea in action. What I'm going to do is draw a real circle, and I'm going to cut off a part of it. So that way I know this is a real circle. And what I'm going to do is that I'm going to choose different points on this circle. Remember that the velocity vectors between each frame are the same as the displacement vectors. So between each dot is a straight line that represents the direction of the velocity. Now, if I want to find what the direction of the acceleration is, I can take any set of 2 vectors. This is where I begin, and this would be my final velocity. So I can find out what the acceleration is at this point as it's moving between, say starting from 0 to 1 to 2. I can find out what the direction of that acceleration is by performing this vector subtraction that we did earlier. And here's what that's going to look like. I first need to take my final velocity vector, and then I'm going to subtract the negative of my initial velocity vector. It has the same length, but it points in the opposite direction. Therefore, my acceleration vector will point here like this. And this will be the direction of the acceleration at point 1. I can repeat this process to determine the next acceleration. So these are no longer my initial and finals. Now I'm going to begin here with this initial velocity, and it's going to end with this final one. So all that I do is follow the steps. Here I'm going to take my initial velocity, and then I'm going to subtract my initial velocity. So it points in that direction originally, but to subtract it, I'm going to make sure it points in the opposite way. So my acceleration vector will start here and point in this direction. Notice the pattern here. When an object is traveling in a circle, the accelerations are always pointing towards the inside. Let's do this one more time. So this vector will be my initial velocity, and this one will be my final velocity. To find the acceleration, I'm going to take my final velocity piece, that's my final, and I'm going to subtract the initial one. Here is the normal initial one, but to subtract it, I'm going to make sure it points in the opposite direction. It's going to point upward. So my acceleration is going to start from the beginning and point in the direction of this vector. And that is the acceleration of this next piece. Like I said, notice how they are all pointing towards the center. And this is going to be an idea that we're going to be coming back to when we talk about circular motion. Lastly, let's end with a try it yourself problem. So here we have a circle, and here we have several points on that circle. I'm going to call this point 1, point 2, point 3, and point 4. The question for you is, at which point would an object experience a downward acceleration? This is going to wrap up our exploration of motion in 2 dimensions. Today we focused heavily on the ideas and concepts behind motion in 2 dimensions. Later, we're going to get into more problem-solving strategies applying these concepts. Thank you for being a part of the College Physics series. I look forward to seeing you in the next lesson.